Welcome to SysAdmin. In today's video, we are going to explore multiplexing methods. Whether you're managing a massive enterprise environment, troubleshooting a congested network, or just setting up new server infrastructure, understanding exactly how data travels from point A to point B is absolutely fundamental. We're going to look closely at how modern networks solve a massive, everyday logistical challenge, getting multiple signals to share a single transmission medium without stepping all over each other.
Here is our roadmap for today. We'll start with the core of multiplexing. Then, we'll cover Frequency Division Multiplexing, Wavelength Division Multiplexing, Time Division Multiplexing, and Statistical TDM before wrapping up with a quick summary. Let's get right into it.
Section 1. The core of multiplexing.
So, let's start with the big picture. In a real-world enterprise environment, you might have hundreds or literally thousands of devices, workstations, servers, VoIP phones, all trying to communicate with the outside world at the exact same time. Obviously, it's completely impractical, not to mention insanely expensive, to run a dedicated physical wire for every single transmission. We have to share the available transmission mediums. And that brings us to our core definition, multiplexing. It's the networking technique that enables several input signals to be combined and replaced by just one output signal. This allows two or more simultaneous transmissions to happen over a single shared medium. But there's a strict rule here. To avoid total chaos and data collision, all of these signals absolutely must differ in some way. They either need to occupy a different frequency slot, a different wavelength slot, or a different time slot.
Think about the basic architecture of this process. On the sending side, you have multiple inputs coming into a device called a multiplexer, or MUX for short. It's kind of like an on-ramp where multiple lanes of local traffic seamlessly merge onto a single high-speed highway. This single link carries all those channels across the network. Then, on the receiving end, a demultiplexer, or DMUX, acts as the off-ramp. It carefully separates that combined signal right back into the original individual outputs.
Now, in practical networking, there are 5 major methods used to accomplish this. We've got Frequency Division Multiplexing, Wavelength Division Multiplexing, Time Division Multiplexing, Statistical Time Division Multiplexing, and Code Division Multiplexing. For our explainer today, we're really going to focus heavily on those first 4 because they represent the fundamental progression of how we manage data traffic across various physical mediums.
Section 2. Frequency Division Multiplexing, or FDM.
So, how does FDM actually work? Well, the overall bandwidth of your transmission medium gets divided up into distinct, non-overlapping frequency bands, or slots. At the sender side, each incoming message is modulated into its own specific frequency slot on a common carrier. They all travel together, essentially stacked by frequency, across the medium. Then, at the receiving end, the DMUX demodulates these specific frequency slots to reassemble the original separate messages.
To make this a bit more concrete, you actually interact with FDM every single day. Radio and traditional over-the-air television broadcasting are perfect examples of unguided FDM transmission. The signals travel right through the air, and you tune your receiver to a specific frequency to catch a specific station. Cable TV uses the exact same principle, but it's a guided FDM transmission, meaning the different frequency slots travel safely contained inside a physical coaxial cable.
Now, put on your system administrator hat for a second. FDM has some clear pros and cons. The biggest advantage is that transmitters can send signals continuously, and you don't need any complex, dynamic coordination between the devices. However, the disadvantages are pretty significant for modern data networks. FDM is inflexible. The number of subchannels is predetermined, and adding more usually means you need entirely new multiplexing hardware. Plus, frequency is a very scarce resource. A radio station might broadcast 24/7, but data communications are often really bursty. If a device has a dedicated frequency channel but goes idle for a few minutes, that frequency slot just sits there, completely unused. It can't be dynamically shared with another device that might be desperately trying to send data.
Section 3. Wavelength Division Multiplexing.
Okay, to overcome some of those strict limitations of FDM, we step up to technologies designed for much higher capacities. WDM uses essentially the exact same general architecture as FDM, but it applies it to the realm of fiber optic communication. So instead of dividing radio frequencies, we are dividing the actual wavelengths of infrared light into specific slots. Think of it like a prism. Each specific color or wavelength of light acts as a completely separate data channel. These different colored light beams are combined and sent simultaneously down a single-mode fiber optic cable. At the other end, a wavelength demultiplexer acts like a reverse prism, splitting the colors back out into their original separate data streams.
A really crucial point here is that WDM enables absolutely incredible amounts of data to travel over huge distances, but it does require some specific infrastructure. Because light degrades over long physical distances, WDM networks require optical amplifiers. These are typically placed tens of kilometers apart, and they boost all the different wavelengths simultaneously to keep the data moving. Fun fact for you, thanks to WDM, a single modern fiber optic cable running across the ocean floor can carry tens of terabits of data per second. That's literally enough to stream millions of HD movies at the exact same time. Also, it's worth noting that light beam modulation is poorly suited for analog signals, which makes WDM primarily a powerhouse for digital networking.
Section 4. Time Division Multiplexing.
All right, so FDM divides things by frequency, and WDM divides by light wavelengths. Now, let's completely shift gears and look at how we can divide a medium using time slots. In TDM, all the sending devices actually use the exact same frequency, but they do it at different points in time. The signal beam is divided into fixed, equal-duration time intervals, known as time slots. Everyone simply takes turns. For example, if we have 3 devices, A, B, and C, signal A gets time slot 1. Then signal B gets slot 2. Signal C gets slot 3. Then it loops right back around. A gets 4, B gets 5, C gets 6, and so on. Because the slots are strictly fixed and predictable, there's no buffering or flow control needed on the line, and an error on one channel doesn't mess up the others.
But basic TDM has a pretty glaring weakness. Imagine a scenario where a couple of devices have inserted data into their assigned slots, but the other devices on the network are just sitting idle. They have absolutely nothing to send. Because basic TDM uses rigid, fixed assignments, those time slots still cycle through, but they travel across the network completely empty. In a modern enterprise network where data is incredibly bursty and unpredictable, this results in a massive, massive waste of potential bandwidth.
Section 5. Statistical TDM.
So, how do we fix that inefficiency? Well, network engineers came up with a much smarter approach. Statistical TDM, or STDM, completely solves the empty slot problem of traditional TDM. Instead of rigid fixed assignments, STDM transmits data in packets. When devices actually have data to send, those packets are collected and stored in a common buffer. The multiplexer then uses intelligent, specific scheduling rules to dynamically assign time slots only to the devices that actively have data waiting in the buffer. No data, no time slot. This dynamic allocation makes STDM the absolute most efficient multiplexing system available. However, because it requires memory for those buffers and processing power for the scheduling, it's naturally the most costly method to produce and implement.
Section 6. Summary and key takeaways.
We've definitely covered a lot of ground today, from radio frequencies to fiber optic light to dynamic data packets. Let's bring it all together for a final rapid-fire review. FDM divides a common medium into dedicated frequency slots, perfect for constant broadcasts like radio and TV, but a bit inflexible for bursty data. WDM applies that exact same principle to fiber optics, dividing data into different wavelengths of light to achieve massive throughput over huge distances. TDM shifts the approach to taking turns, assigning fixed time slots on a single frequency, though it risks wasting bandwidth when devices sit idle. And finally, STDM solves that waste by using buffers and dynamic packets, ensuring that the network is always operating at absolute maximum efficiency.
So, I'm going to leave you with this question to ponder as you look at your own networking environments. Which multiplexing method is best equipped to handle the chaotic, unpredictable traffic of the modern internet? When you really think about how web browsing, streaming, and enterprise applications constantly burst and pause, the value of dynamic systems like STDM becomes incredibly clear.
If you found this helpful, subscribe to SysAdmin Academy and continue building your IT expertise.